Hello and welcome to FEM Expert. Today we will present you a basic tutorial in which we will present you how to model and analyze a T-junction model with shell type elements in Ansys. We'll start with this little schematic idea of what we'll simulate today. And what we'll have is a T-junction with two different profiles. The first profile will be a 40 by 40 by 3 millimeter square hollow profile, and the second one would be a 40 by 80 by 3 millimeter rectangular profile. The first one, the 40 by 40 would be on the transversal beam, and the 80 by 40 will be on the longitudinal beam. Both of these beams would have 1 meter length, and they'll be joined at the middle, and the model will be restricted at both ends of the transversal beam. So we will start with we'll continue with the Ansys environment, and for this tutorial we will use a little bit different approach. As we said, the transversal beam is going to be a 40 by 40 by 3 millimeters. If we do it throughout the extraction of the medium fiber, that will be a 37 by 37 millimeters with a thickness of 3 millimeters. So what we'll do today is use a different approach. We will go to Preprocessor, go to Modeling, and we're going to create an area, actually a rectangle by dimensions. And here we will have the first coordinate on the x-axis is 0, and the second one is 37 divided by 1000. On the same thing on the y direction. By doing so, we will create an area which has, if we go to a global plot, it has lines and key points. We don't want to use the area, but we want to keep the lines and key points. So what we'll do now is go to delete, and we're going to delete the areas only. We're going to select this area, hit OK, and when we refresh, we're going to see that we have the rectangular profile of 37 by 37 that we needed. Now we're going to extrude this profile, and then I'm going to show you how to use a similar approach for the longitudinal beam. We're going to first copy one of the key points on the corner. I'm going to hit OK, and we're going to copy it on the Z direction on 0.5 meters, because our whole beam has a length of 1 meter. So we're going to apply this. We're going to select again a point is the fourth point, because it's the smallest of this area. We're going to hit OK. We're going to OK and do the same thing at minus 0.5. Now if we go to the isometric view, what we'll see is we're going to go on the global plot, G-plot, and go into the isometric view and fit view. What we have is the profile and the two key points that we just created. Now we're going to create lines. What we're going to do is obtain this profile by extruding this section. So what we'll need to do is have lines. In order to do that, we're going to create the lines, the guideline for the extrusion. We're going to create lines, straight lines between this key point and this key point, and this key point and that key point. After we have done that, we're gonna perform the extrusion as we did in the other tutorials, and for that we're gonna go to Modeling, Operate, Extrude, Areas. We're gonna extrude lines along lines. So we're gonna select the 4 lines of the profile, hit Apply, and select the direction. Then we do the same, select the 4 lines of the profiles. I'm gonna hit this one again and see the results. So when we use the extrusion option, what we see is if we use the line list, pick, this allows us to list all the lines that we have. And you'll see that if you pick up here where you had the 2 lines of the extrusions, there are 2 lines on top of each other. This can create problems and is not recommended. Actually, if you go to this other side, the same thing, we do the same thing, line list, pick, We hit here, no double lines. We hit here and there's two lines on top of each other. So in order to avoid this problem, what we have to do is a merging, which can be done as we saw on the other tutorials on the numbering controls. Merge items. Here we have to select key points, we hit OK, and then when we do the same line list comma pick, sorry, that's a little mistake, line list comma pick, if we select this, there's only one line, and here there's only one line. I'm gonna go again to the global plot, and so far we have the transversal beam. Now we want to create again, now we want to create the beam from this area, and what we could do here is we could use different methodologies. We could cut using the working plane, cut the area that we're interested in, or we can just simply create key points, lines, area. It depends on each methodology. So today what I'm going to show you is how to use a clever idea and keep the same procedure that we used before. First, what we're gonna do is get the workplane, offset the workplane to key points, and we're gonna put the workplane here. The second thing is we're gonna rotate the workplane. In order to do that, we have to go to offset workplane by increment, and we're gonna rotate the workplane 90 degrees around the y-axis so that we have the XY plane on here. So now what we want to do is create a 77 by 37 rectangle. So how do we do that? We could use, as I said, we could cut things, or what we're going to do today is use the same procedure that we used before. So we're going to go to modeling, create, areas, rectangle, by dimensions. So now what we have, on the y direction, we have the same dimensions. We have a 0 and a 37 divided by 1000. On the x direction, we have minus 77 divided by 1000 divided by 2, because we have to have half of the profile on the left and half of the profile on the right. So we're just simply going to put divided by 2000. And on the right is 77 divided by 2000. When we do that, we will have the profile created. As you can see, there's two areas there. We can go and plot the areas, and you'll see that, well, you can't really see this thing properly. There's no different colors, but we know that there's another area. We can list the areas, and we'll see. We go back a little bit and do this a list from area list, comma pick, and if we hold the mouse, we'll see there's one area, then there's another area, and there's a third area. These areas do not share anything right now. They're just on top of each other, so we have to do something with them. We could cut them, do other things, merging, but we're going to use some of the operations, the Boolean operations, and among them we have the overlap, which is a very cool option. The overlap, we're going to go to areas. I'm going to select this one, this other one, and the third one, and click OK. If the areas are properly created, what will happen is that the program will, if we do an area list now, the program will merge those areas and make cuts, divide them, so they are a total of 4 areas instead of 2. So now we're going to repeat a little bit of the procedure, but to make it easier, we're going to go to Workplane and change the active CS to Workplane. So this means that the coordinate system is going to be put into or transformed, or is going to be we are going to be using the coordinate system that we have with the Workplane in this moment. So if we want to create a point that goes from here, a key point from here at 1 meter, we have to copy it on the Z direction at 1 meter. For that, we're going to do the same procedure as before. We're going to copy a key point. Let's choose this one. We're going to hit OK, and the offset on Z will be 1 meter. Why do we have that? Let's go to gplot again. Because the z direction on the work plane is on the way of the x direction of the global coordinate system. So now what we have to do is, again, modeling, create lines, straight lines, pick up this point, pick up this other point, and again we're gonna go to operate extrude lines along the lines. We can zoom in here because it might be a little bit more complicated. 1, 2, 3, 4, 5, and 6. We don't need the middle one, there's no middle line there. We go back to the zoom, hit OK, select the direction, and we hit OK. And there we go. We have the 40 by 80 millimeter profile junction. At this point we have a problem because we haven't done the merging, so we're gonna have to do the merging again. Numbering controls, merge items, key points, we hit OK, and our model is properly made. We can go and change the active CS to the global Cartesian, and we can take off the working plane right now. So at this point we have the model. What we have to do is define the element types. Edit, delete. We're gonna add shell 181 for nodes. We're gonna hit OK. We're gonna close this menu. Now we don't have real constants with this element type, so we're gonna go to the material properties, material models. We're gonna define a structural linear elastic isotropic material, 2.1 exponential 11 Young's modulus for steel, and 0.3 the Poisson's coefficient. We're also going to put density, 7,800 kilograms per cubic meter, and we're going to close this. Now, well, what else we have to do is define the sections. For the sections, we're going to under the sections area, shell, layup, add, delete. Here we're going to put a name. We're going to say 3 millimeters. The thickness is going to be 3 divided by 1,000. The material ID and the rest of things are the same, and the section offset is going to be as default midplane. That means from the midplane that we have created, the thickness is going to be similar or assigned half of it towards the outside and half of it towards the inside of the profile. Now we hit OK, and at this point the next step is to tell Ansys that these bars, or these models, or these shells, or these entities that we have defined have these properties. So to do that, we're going to go to meshing, mesh attributes, picked areas. I'm just going to pick all now because they're the same. And we have material number 1, their element real constant no define element type 181, which is the one that we need. The coordinate system, we don't need it, and the thickness is 3 millimeters. Hit OK. And now the next step is to create the meshing. For the meshing, we're going to use we're going to do it manually this time. We're going to go to size controls. We're going to manual size areas. We're going to put on all areas. The size of the meshing is going to be 10 millimeters. So it's 10 divided by 1,000. I'm going to hit OK. And now for the meshing, we're going to go to mesh and do it with areas mapped by 3 or 4 sides. By 3 or 4 sided, we're gonna pick all, and there we go. We have the high quality meshing done, and our model looks pretty good right now. I'm gonna go and do the plot lines so I don't have all the elements and the model moves freely. Now the next step is to define the load cases, the restrictions and the load cases, and proceed to the simulation. So I'm going to go to solution, analysis type. The new analysis has to be static. By default is static, so you can avoid this step. Then you can go to define loads, apply structural displacements, and we're going to apply displacements on lines. We're going to do it once here. All degrees of freedom and the value 0. And we're going to do it on this other side. All degrees of freedom 0. Okay, so now what we have to do is put a force. We're gonna input forces on key points. We're gonna put on these 3 key points, we're gonna put 3 forces downwards, which are gonna be on the y direction, minus 100 Newton each one of the forces. So now that we have that model, we go back, we go to general, we can go and simulate it. Solve, current ls, okay. We wait a little bit until the solution is done. After that, we go to general processing, we read the results, last set, or you can do it just first set, doesn't matter. At this time, it's irrelevant. We're gonna plot the results. First, we're gonna do the contour plot, nodal solutions, degree of freedom, summation of displacements. As you can see, this beam is very rigid, so there is some kind of twisting that is not quite obvious, but the biggest deformation or displacement takes place at the end and the smallest at the transversal beam. We're gonna do again we're gonna see a rotation vector sum, and now as you could see, there's not too much of a rotation on the longitudinal beam, but there is a lot of rotation on the transversal beam. We're gonna go again and plot the stress, the von Mises the stress, okay, and as it would be normal, the stress is concentrated around the beam, around the junctions and around the embedments. And finally, we're going to look at the vector plot, predefined, degrees of freedom, translation first. As we said before, this can be very handy when you need to analyze a more complicated situation. You can see the vectors, the displacement vectors, and clearly see that the beam is moving. And we're going to try the rotation too, to see if we can see here the rotation vector. You have to understand these are rotational vectors. It takes place a rotation that's almost equal on the longitudinal beam, and on the transversal beam it varies due to the different colors and magnitudes. So this is pretty much what we have for today. I'm gonna go to quit, no save, and now you know how can you use some more features of Ansys to model shell type elements. Also, you got some clever ideas on how to create a shell, delete it, and use the remaining entities that shell created. And finally, we hope you enjoyed this presentation, and we would like to thank you for your attention. For more tutorials, please visit our community and follow us on the social media.